In this video, we will revise some important concepts of information theory. And these concepts are important when we study the expressions of capacity in wireless channel and particularly for the AWGN channel. So the first definition, first important concept is entropy of the source. Now, entropy of the source gives us the inherent randomness in the source, or we can say it is the measure of information or uncertainty. And it is also, this entropy is also useful in describing the average number of bits, zeros and one, that would be required to encode the source in a more efficient way. So we can say that, let's say we have a three source, x1, x2 and x3, and let's say these bits are used to encode these symbols. So for x1 we require 3 bits, then x2 we require 4 bits, and for x3 we require 5 bits. And if we try to compute the average, we will get 4 bits. So entropy tells us on an average we required 4 bits to encode the source or the data symbols x1, x2, x3. And it also gives us the minimum number of bits that are required to encode the source. Entropy is represented by h of x, where x is a random variable which takes on the values from the set mathcal x and is given by this formula. Here p of x is the distribution of x. Since we are talking about discrete random variables, then p of x is the probability mass function log 2 p of x. Now there are two things, either we can take log 2 or we can take natural log. If we are considering log 2, then we have entropy is represented in bits, and if we are considering natural log, then we say entropy is in nats. And also we know that this p of x, the value of p of x lies between the 0 and 1. So accordingly we have p of x less than equal to 0, and so we have h of x is always greater than 0. That means for a discrete random variables or for the discrete sources, the entropy is always greater than equal to 0, or it is a positive quantity. The next definition is joint entropy. Let's say we have a pair of random variable x and y, and they are distributed according to the joint PMF px, y. Then according to the definition of entropy, we can write joint entropy in this particular way, which is the summation over all distribution of x over all y, then p of x, y, and log 2 of p of x, y. And this joint entropy tells us the entropy when the two sources have certain entropy together. Next is conditional entropy. Let's say we have two random variables x and y, and they are distributed according to px, y. This entropy of y by x specifies what is the entropy of y given the entropy of x, and this is represented in this form. This is positive summation over x, distribution of x into entropy of y when x takes on a particular value x. And from entropy formula we know that this h of x is equal to minus summation over x, distribution of x, to log 2 of p of x. Now if we substitute this y by x into this expression, and we can substitute this entropy of y by x into this form, and then on solving, what we get is this: the entropy of y by x, that is conditional entropy, is defined as the negative sum over x sum over y joint distribution of x comma y into log of distribution of y given x. And we have the chain rule also that specifies the joint entropy of x comma y is equal to hx plus hy by x. And we can also prove this, because this is true, and we can also prove this using, let's say, h of x comma y. The entropy of x comma y is given as minus summation over x comma y p of x comma y log 2 of p of x comma y. And from the Bayes theorem we know that p of x comma y is written as p of x into p of y by x. Now if we substitute this into this formula, what we get is minus summation of x comma y p of x comma y log 2 of p of x into p of y by x. And if we solve this for log, if we open this log term, what we get is minus summation of x comma y p of x comma y log 2 of p of x minus summation x comma y p x comma y log 2 of y by x p of y by x. This is the entropy of x. So we have this hx here, and this is the entropy of y by x, and so we have h of y by x. So from the chain rule, what we get is the joint entropy x comma y is equal to entropy of x plus the entropy, conditional entropy h of y by x. Then the next term we have is relative entropy. Relative entropy is the measure of the distance between the two distributions px and qx, and this is represented by d pq. So basically this relative entropy is the distance, and it is defined as Kullback-Leibler distance. And how this relative entropy is given? It is given by this form: d of pq is equal to summation over x, the distribution, the first distribution of x, that is p of x, log of px by qx. And this is not equal to d of qp, because in this case what we have is summation over x q of x log of q of x by p of x. And if you solve this expression for the given distributions, these two expressions will not come up to be the same. So we say the distribution, the d of pq is not equal to d of qp. And also, since this is the distance, relative entropy is the distance, and distance is always greater than 0, so d of pq is always greater than equal to 0. So next definition is mutual information. Now if we have two random variables, random variable x and random variable y, that are distributed according to the joint probability mass function px comma y and the marginal probability mass functions px py, then the mutual entropy is the relative entropy between this joint and the product of the marginal. That means mutual information is the relative entropy between the distribution px comma y and the product px py. So what we have is the capacity. When we talk about capacity, it is represented in terms of mutual information, and mutual information is represented in terms of relative entropy, and relative entropy is represented in terms of entropy. So as a result, we have this relation. So when we need to study capacity, we need mutual information, and for mutual information we know we need to study the relative entropy, and for relative entropy we must understand what is entropy. So if we try to expand this mutual information using the definition of relative entropy, so we have P of x comma y log of Pxyy upon Pxpy, because the relative entropy was summation over x P of x log of P of x by Q of x. So it was the distance between the distribution Px and Qx. And now in this case, we have Px comma y and Px Py. Thus, it can be represented in this form. So then using the Bayes theorem, if we try to expand this Px comma y, we get Px by y into Py. So here this Py gets cancelled out. And if we try to expand this logarithm, because they are in division form, so we can write it like this: log 2 P of x by y minus log 2 P of x. So then if we substitute this into this expression, what we are left with, this form. This is the entropy of x, and this is the conditional entropy h, negative of conditional entropy h y by x. So since here we have put it x comma y, probability of x comma y as p x comma y, x by y into p of y, we can also write it in other form, p of y by x into p of x. And if we try to substitute this here, then what we get is px will get cancelled, and here we will have p of y, and here we will have p of y by x. So in this case, we can write it as entropy of y minus entropy of y by x. So we can get these two formulas easy. And then again from the chain rule, we have information x comma y is equal to hx plus hy minus h of x comma y. So this can be obtained easily by using this chain rule. H of x comma y is equal to h of x plus hy by x. So from here, if we can take out hy by x, it will be equal to h of x comma y minus h of x. And if we substitute this hy by x here, then we can get this formula easily. So these were the three important formulas for the mutual information between x and y.